Okay. Now, let's start with a significant figure first. Okay. Um, so if I say 0.02, how many significant figures do we have right here?
3.
1.
One. If I say 0.101,
3.
this is three significant figures. So for the zero rule, right? The zero is being calculated as is being considered as a significant figures if it's located between two non-zero. And then if you have like a 2.0, how many significant figures are there?
2.
There are two significant figures. Okay, so for the significant figures, any of you have problems? No. Okay, next. We go with the uncertainty. So the first one is I'm going to discuss about the absolute uncertainty. So the notation for the absolute uncertainty is usually written in a shape of like a triangle. It can be triangle of x or triangle of y. So usually with the triangle things. And there are rules in writing absolute uncertainty. So, okay, I just show you an example first, okay? So usually in physics or chemistry, when you write your report, right, you have to write the x plus minus uh, the change of x. That is not the change actually, that is the absolute uncertainty. So x is the measurement that you are checking. X is the absolute uncertainty of your measurement. So before we discuss like how do we get the x or the change of x, I want to discuss about the way or the rule in writing this first again. So let's say one student write 5 plus minus 0.2 centimeter. This is not right. This is wrong. Why? Your absolute uncertainty should have the same decimal place with the measurement that you want to explain. So I see your absolute uncertainty, you write up to one decimal place. So means I expect you to write your measurement as a 5.0 plus minus 0.2 centimeter. This is the right one. So if you write your absolute uncertainty up to one decimal place, then your measurement should have a one decimal place. So you should add a zero. Okay. Then, for example, probably the device that you are using has an absolute uncertainty of 0.05 centimeter, for instance. Then you have to write it as a 5.00. Do you understand though here? This is the right one. Also, another example, let's say your uncertainty, your absolute uncertainty is quite big in this case because probably you are measuring like a change in height in like mountain areas or how. So your uncertainty, your absolute uncertainty is, let's say you run in 100 meter, for instance. So when you write an absolute uncertainty of 100 meter, means what I understand is you if you write in this way, it means your actual reading should be rounded off to the nearest meter. So for instance, you show me a reading of a 3 415. I cannot accept this. Because when you write like this, what I understand is you want to round it off to a nearest meter, nearest hundreds, I mean. So for the absolute uncertainty, I never, I mean, if you are writing a report, yeah, not like when you calculate or answering exam questions, okay? If you are writing a report, right, usually if you want to write it to the nearest 100, you can write a plus minus 100, plus minus 200 or 300 and so on. So that's how the person understands that you are running it out to the nearest 100, okay? So it means if you want to write it like this, then I would want to see our answer like a 3,400 plus minus 100 meter.
So it's like plus minus 200, 300, we might get to the nearest 300 or still 100.
No, we still, okay. So usually it's like one decimal place, two decimal place, or you still call it as a hundreds or thousands. So for instance, if you write a plus minus like a 500, I still consider this as rounded up to the nearest hundreds. So it will be good to see you write something like, for instance, you write a 10,200. This one is acceptable. This one is accepted because I understand that this reading, this one has been also rounded off to the nearest hundreds, right? Okay. What is the effect if I don't learn this? If you take IB, you will have a problem in writing your report and your IA, definitely already. If you take A level, you will have a problem in answering paper 3 and paper 5. Also the other components. So the other components also, they will ask you about like the rule of writing this. So there is no way to avoid this, no matter which syllabus that you are taking. Do you have any questions that you want to ask until here?
Why is this needed? Wouldn't it be better if you give exact numbers, not round it off?
Sorry.
Why do they teach us this? Like, wouldn't it be better if we just like leave it as 3415? Wouldn't that technically be more accurate?
Oh, it will be very, you can say it's not scientific, but in my opinion, it's messy if you like write so many significant figures in your report. Like when people are reading your report, right, they are confused because you have a wide range of significant figures. So you have to decide you want to write in 2 significant figures only or 3 or how.
Okay.
Would you please take a photo of this first? I'll give you time to write later. Okay. Now, the second type of uncertainty is fractional uncertainty. Fractional uncertainty is your absolute uncertainty divided by your measurement. Done. So just leave it like that. Okay, so when someone say, what is your fractional uncertainty? Means he asked for that. The next type is percentage uncertainty. So percentage uncertainty is you take your fractional, uncertainty and you multiply it with 100. So like you change it to percent in a percentage form. So there are 3 types of uncertainty. Do you understand until here?
The fractional uncertainty is what gets absolute certainty over.
Your absolute uncertainty over the measurement that
Okay.
you are taking. Okay, then I will continue to the third point. Yeah. So just now the second points we are discussing about the types of the uncertainty, right? Now the third points. We're gonna discuss like how to get the absolute uncertainty. So actually, there are several ways here. The first one, the most basic one, is the absolute uncertainty is usually half of the smallest measurement. Usually, like, okay, for example, meter rho. If you use your ruler, what is the smallest measurement that you can read at your ruler? Up to 0.1.
0.1 centimeter.
Centimeter. So it means the absolute uncertainty for a meter rho is okay. So you have a 0.05 centimeter. So that's thermometer. For example, thermometer, your lab thermometer can measure up to how many? For example, the smallest unit is 1 degree Celsius. So means the absolute uncertainty is 0.5 degrees Celsius. So if you are using beaker glass in your chem experiment, beaker glass usually multiple of like a 10, right? 10 milliliter. Yeah? So the absolute uncertainty is 5 milliliter. Understand, yeah? Until here. This is a common one. But if you are doing an experiment, probably in the future, you might meet a case where the uncertainty is unknown. I don't know like what device, but probably you are using, for instance, you check the intensity of sound in physics lab. Okay. So you have several experiment. You have, I mean, you take several readings, right? So you have like x1, x2, until x5. For repeated readings, you can just simply take half of the x maximum minus the x minimum. So for repeated readings that you don't know the uncertainty of the device, you can just choose the maximum reading that you get, you subtract it with the minimum reading, and you divide it by 2. That is how you get the absolute uncertainty. Do you have any questions that you want to ask until here? No. So means you still can't understand.
So the X max is the like the X factor.
Your experiment, your reading, the reading that you are taking. What is the maximum reading? You understand?
No, not really.
So you are checking the intensity of a sound, right? And then probably you are taking the reading several times, like how many decibel at there. So yeah, after you get these all readings, right? After you get these all readings, then you don't really have to care about the uncertainty, is it written in the device or not, because you can just choose from the readings that you repeat, right? What is the maximum and what is the minimum? You just subtract them and you divide by 2.
Okay, I understand.
But then, right, you have to be wise also. I I never see uncertainty of 0. And for me, it also does not make sense. How can your maximum and the minimum reading is exactly the same? Let's say you do it for 8 or 10 times and then it's exactly the same, or all of this does not make sense. Okay. Okay. So far until here, you have any questions that you want to ask? No, okay, I give you time to write down first, yeah. Be right back. Okay. Number 4, we're gonna discuss about the rule in the uncertainty. So basically, it's being divided into 2. If I teach too fast, let me know, okay? So the first one is we're gonna discuss about the subtraction and the addition rule. So for example, this one probably simple, yeah. Let's say the experiment is like about measuring length of a pencil. So actually, if you measure the length of a pencil, there are 2 readings that you have to take. Why there are 2 readings that you should take? The first one is the starting point, and the last one is the end point. You should read at the beginning and you should read at the end, right? And then actually you subtract both of them, isn't it? To give you the length of the pencil. So when you are reading at the starting point, let's say you start from 0. What is the uncertainty of meter rule just now?
0.05.
Yeah. So I expect you to write a 0.00 plus minus 0.05 centimeter. It looks simple, yeah, because if you don't obey the rule, if you write 0 plus minus 0.05, wrong already, your score will be deducted, that for sure already. So let's say the end point, the length of the pencil is at around like 8.2. You also have to write 8.20 plus minus 0.05 centimeter. Then you will write the length of the pencil is equals to, you subtract them, right? So it's still 8.20 centimeter, is it? Now, how are we going to deal with the absolute uncertainty for addition or subtraction relation? For addition or subtraction, the rule is the absolute uncertainty is always been added. So I can say the absolute uncertainty is 0.10 or 0.1 centimeter. Even though you do subtraction, the absolute uncertainty cannot be subtracted. It should be added. So you have 0.05 and you have 0.05. That's why you're going to add it up. So now your answer, you can just write as 8.2 plus minus 0.1 centimeter. And it will be wrong if you write 8.2 plus minus 0.10 centimeter. This is wrong. Why? How many decimal places do you have at the absolute uncertainty if you write like this? You have 2 decimal places. But then the reading only have 1 decimal places. So it is wrong. So you just need to write like 8.2 plus minus 0.1 centimeter. For the
So
first
8.20 also can as well.
If you want to write as 8.20 plus minus 0.10 centimeter, for instance, it will be wrong also actually. Why? Let's say if you use a meter rule, can you read up to 2 decimal places?
No.
Yeah, so I don't suggest you to write like that also. I will just suggest you to write as 8.2 plus minus 0.1.
But the endpoint one, we have to write the 2 decimal places.
Oh yeah, when you're still taking the data, this one, right, you have to write like this when you are taking the raw data.
How about the result? The length of the pencil.
No, you just can write as 8.2, that's enough already.
Okay.
Okay, so for example, let's say the second one is you are measuring volume of an acid. So it means your initial, if it's empty, if you use beaker glass, if you use beaker glass, just now your beaker glass from your previous one is 5, right? 5 centimeter cube, right? Or 5 milliliter, isn't it? So the initial is like 0 plus minus 5 milliliter. And then you fill it until the final, you fill it at 50, for instance. So it's 50 plus minus 5 milliliter. So it means when you want to write the volume, you subtract both of these, right? You subtract both of these, isn't it? So it means still 50. But then what you do to the absolute uncertainty?
Add it.
Yeah, add it. So become plus minus like how many milliliter right there?
10.
10 milliliter. For the initial, you also have to be wise here. If you think it's totally empty, it will be fine. If you want to write it as if you think it's totally empty at the first case, you can write it as 0. Okay. So I mean in this case, it will be plus minus 5 only. So why will it not be totally empty? Yeah, for instance, you repeat your experiment. So you use the beaker glass already, right? And then you wash it. But probably it's not dry enough. If you are very sure that your beaker glass is like totally dry, then you don't need to put any uncertainty. That is fine.
So they won't mark us wrong on like that or anything like that.
No, but technically, if you always repeat your readings, then you always have to show.
Okay.
Any questions so far until here? No. Okay, so let's say for
Sir,
instance,
can you repeat why 8.20 plus minus 0.10 centimeter is wrong?
which one? The pencil one or the volume of the acid?
The pencil one.
Because you wanna add the absolute uncertainty. So it's 0.05 plus with 0.05. That's why it becomes 0.10.
No, I mean why is 0.10 wrong but 0.1 okay.
If you write it as a 0.10, then your reading have to be 8.20 also, 2 decimal places. But if you're using a ruler, usually you can just can read up to 1 decimal place.
Okay.
Okay, so let's say you measure the volume of a stone by using a measuring cylinder. So if you use a measuring cylinder and let's say initial is you already fill it with water, so measuring cylinder can measure up to 1 centimeter cube, right? So let's say initial you fill it at 10, so means you have 10 plus minus 1 milliliter. Then after you drop the stone into the measuring cylinder, you get a final reading, let's say at 14, so still plus minus 1 milliliter. So means the volume of the stone is, you subtract it, right? And then so add the uncertainty.
Oh.
Yeah. Oh, sorry, 0.5. Yeah, 0.5. So means my initial supposed to be written as a 10.0 plus minus 0.5 milliliter. And the final would be 14.0 plus minus 0.5 milliliter. So means the volume of the stone is equals to 4, and then you add the uncertainty. Do you understand until here? questions? No. No. Okay. Let me ask you a question, sir.
Wait, sir, how do you get like the actual value? I mean, like
Which
you, the like when you first look at it without the uncertainty, like the 10 and the 14, do you round up or round down in that case?
Sorry. What is the round up or round down?
For example, you get a meter roll, you get in like between 14 and 14.1, but then you don't know where it is. So do you just write 14 or 14.1, then the plus minus?
I don't see as a problem any of that you want to take because however you also will repeat it, right? You find the average. Right?
Okay.
Okay. Okay, Annabelle. For example, our next discussion is like. So let me ask you: if you want to measure the 50 centimeter cube of acid, if you pour it like a liquid twice, so you pour 25 first, you read, and then you add another 25 again, that also will give you 50. Or you just pour it once up to 50 directly and you read. Now, these two ways of doing experiment will give you different absolute uncertainty. Yeah. I mean, even though you get a 50 centimeter cube at last, but the value of the absolute uncertainty is different. Why? Okay, let's discuss about the 4A first. You measure the first 25 centimeter cube. So, and let's say you are very sure that at first it's totally dry. Then I can say, okay, you can start with the initial as 0, for instance. And then the final, you have 20, 25.0. Let's say using measuring cylinder, for instance. So this is your first 25, right? Anyone don't understand? Okay, then next one, you add again another 25. So at that moment when you add again, it means your initial, before you add it, you already have another 25.0 plus minus 0.5, right? You already have the first 25, right, in your cylinder, right? Then you add again. So, okay, your final amount is 50.0 plus minus 0.5 milliliter. So when you want to count the total volume, I can call this as V1, right? And I can call this as V2, is it? So, however, my total volume, I will add them up together. So it's 50, right? But how much is the absolute uncertainty at there? How many times are you dealing with the absolute uncertainty? The total now become 3 times, right? At first it's totally 0, then you have 0.5, you have 0.5, and you have 0.5. So you have 3 absolute uncertainty. How much is the total? It means the total is 1.5, right? So it means you're going to write your answer as 50.0 plus minus 1.5 milliliter. If you go with that way, okay? Then now if you did it once at 50 centimeter cube, then your answer will be 50.0 plus minus. Means you already have initial 0, right? And your final is 50, right? So how much is the absolute uncertainty that you deal with? It can be still 0.5. So the second method will give you a low uncertainty. So that is better. Do you have any questions until here?
Wait, sorry, so you mean the second method is more accurate? Do you say that just now?
Right. Like for example, the reading is plus minus how many gram, and then if you measure the volume, y plus minus 1, y plus minus 1 just now actually can be plus minus 0.05 because you're going to read twice, that's why it becomes plus minus 1. And then for the temperature, you see the one that he write on the column of the table is plus minus 1 degree Celsius. Okay, so if you look at the volume of the water, you write plus minus 0.1, right? And then the reading is up to how many decimal places? Then he should show up to 1 decimal place also. So if I don't want to write like this way, how? Yeah, no one gonna read your report. Your score will be deducted all. It's as simple as that. Okay. Then why I should learn how to show the calculation? Because right in the report, the standard is how can I know you understand or not? Probably you ask from someone else. So later in like a separated page, right? You don't need to show for all of your experiment, of course, but then you should explain how I get the absolute uncertainty. That's why I tell you there are two rules, right? We only discuss about addition and subtraction. So you're going to discuss about multiplication and division. So in the separated page, you should explain to your teacher how you arrive in this kind of error. Now after you have listed this out, the uncertainty, and you explain how you get it, right? Now you're going to plot. So if I don't want to show the uncertainty, then you cannot show the error bar. No one do a experiment without the error bar. If you take sciences or engineering, you should have an error bar in your data. It's a must. It's just a matter of time when you're going to do it. Okay. Yeah,
So this chapter is also for chemistry.
This is a standard of writing a report. So yeah, the rule can be applied to all sciences and mathematics major. Okay, so at least I show you that it is really you really require this. Yeah, I already show you. Okay, then now I'm going to discuss about the second rule where we have a multiplication and division. For multiplication and division, we have nothing to do with the absolute uncertainty. We only have something to do with fractional or percentage. So you're going to choose between one of them. Okay, so let's say I am doing an experiment in physics. I want to check the value of the gravity. So I want to check the value of a gravity. And then I will set up an experiment like I drop an object from a height of, for instance, like 10 meter. And I observe the time it hits the ground. What is the time taken for it to hit the ground, for instance? So let's say the time you get is around 1.5 seconds. Now this one is your raw data, okay? But then once you type it in your report, you have to like make it good ready. How do you measure height? What you gonna use? Measuring tape, meter rule, right? Probably you can repeat it twice or 3 times, but then of course, you know, right? When you read the height, you will read the initial and the final, isn't it? So you're gonna minus it, right? But then the absolute uncertainty is always been added. So the height, I can say, okay, the uncertainty is plus minus 1 meter, for instance. Depends, yeah. If you use a measuring tape still can read up to centimeter. Measuring tape still can read up to 1 centimeter. So you still can write, for instance, you can write 10.00. It can read up to 1 centimeter. But then 1 centimeter, you divide it by 2. So become half centimeter, right? How many times you should read for one reading? You should read the start and the final, right? So half plus half. How many centimeter you have the total? One, right? But then if you decide to write in meter, yeah, becomes 0.01 meter. So because you are in 2 decimal places, then your actual measurement have to be 2 decimal places. And okay, you measure the time. You use what? For instance, you use a stopwatch. Then your stopwatch, you can report it as 1.50 plus minus 0.01 second, for example. And then let's say you already know the equations. The equations that you are using to check is h equals to half gt square, for instance. So okay, I just put in the formula and then it will be able to count the z, right? So it means I have like a 20 divided by 1.5 square. The z I get is 8.889 meter per second square. For instance, you can calculate this. Yeah, you can calculate, but then what's next? You need to write. To write your result, you need to know the rule, right? So if you are involving a multiplication or a division, the rule is we follow the least significant figures of the other data. What is your other data? Your other data is height and time. How many significant figures are there? You see what the height? 4 significant figure. Yeah, well, for the time, you see it as a 3 significant figures. So if you want to write your answer for the gravitational field strength, you should write it as 8.89 meter per second square. You should write it up to 3 significant figures only. But then, how am I going to write the uncertainty? Until the gravity, understand, yeah? Why I choose 3 significant figures? Because I should have or should follow the least significant figures. Now to calculate the uncertainty, you should make the gravity as a subject. How do you make the gravity as a subject? This is what you get, right? You make the gravity as a subject. Okay, remember the step, yeah? Must make it as a subject first. Then you focus at the power of the variables. What is the power for the height? 1. The power for the time is 2. The other coefficient like pi or 2 or 3 that you have, then just ignore it. So the power times the fractional uncertainty. Understand the number is coming from where? The number or the coefficient is the power. Then what is the uncertainty of the height? Okay, 0.01. Then you can calculate the fractional uncertainty for the gravity. So the fractional uncertainty is just now you have the gravity, right? You have calculated it, right? 8.89, is it? You cross it there. Become product. So what is the absolute uncertainty for the gravity now? 0.1274. How many significant figures? You want to write it just now, your decision? 3 significant figures, isn't it? If you write it in 3 significant figures, how many decimal places do you have from your gravitational field strength? 2 decimal places, right? So your final answer should be 8.89 plus minus 0.13, because you have desired it to be written in 3 significant figures, and when you write it in 3 significant figures, you have 2 decimal places, so your uncertainty also should have 2 decimal places. Okay, if I don't want to learn this, what is the use of learning uncertainty? Okay, so we go back to his plot just now. You see the students draw an error bar. So when you have an answer of 8.89 plus minus 0.13, it means if you have an error bar, the width of your error bar is 0.13. Okay, so if you don't want to learn this, yeah, it doesn't make sense, because when someone questions you, right, what is the significance level of your task? How certain are you with the result? How are you going to answer it scientifically? You cannot just say, I'm quite sure, I'm not sure, I'm very, very sure. You don't have the level of measurement at there. That's why you should know how to put it in numbers. So we talk about the numbers. If no questions, you can write down first. Do you understand if you make the mass become greater, the fraction will be smaller? I use
Yeah.
1 gram, right? If you use 10 grams, then it becomes 0.2 over 10, right? Now, in that case, later when you want to calculate the uncertainty for your concentration, the value will be lesser, is it? If the mass of the solid is greater, your value will be lesser, right? So in another word, I can say you become more certain, is it? Because you have a lower uncertainty, right? Any of you have questions until here? How many significant figures are there, the list that you have? Two significant figures, okay. Then that's why your concentrations, the answer have to be written in 2 significant figures. So it'll be 0.12. So that's why you have a 0.12 plus minus. You run off the uncertainty, become 2 decimal places also. That's why you have a 0.03. So 0.12 plus minus 0.03. Is that clear until here?
Sir, for B, why is the uncertainty 0.1?
Sorry, for what?
For B.
For what is that 0.1? No. Oh, the mass of the empty blah blah. Oh, then I just consider as a 0.1. Like I just give you a random value.
Sir, can you explain from where 0.03 again?
It's actually 0.0252. But then, because the concentration you have decided to write it in 2 significant figures, and in this case, if you write the concentration in 2 significant figures, it will give you 2 decimal places. So your uncertainty also should be in 2 decimal places. That's
Okay.
why you make it become 0.03.
Okay.
The other students have questions?